Let's take a look at a few example problems using the similarity and right triangles concepts that we looked at in the previous video. If you remember, what that video talked about was anytime we have a right triangle, like say triangle PQR here, and we draw the altitude from the right angle down to the hypotenuse, we create two new right triangles, and those two right triangles are similar to each other, and they're each similar to the original triangle that we started with. So in this problem we have that situation happening, and our first job is to find the length of QS right here. Now some people might realize that we could actually just use the Pythagorean Theorem to find that length, and that's true since triangle QSR would be a right triangle, because if there's a right angle here, there'd be a right angle here. We could use the Pythagorean Theorem because we know two of the sides of this right triangle and we're missing the third, so we could use a squared plus b squared equals c squared. But instead what we're going to do is we're going to try and use those new ideas of triangle similarity. So what I'm going to do is I'm going to first kind of label some of the angles in these triangles to show, just to kind of get a grip on what parts of each triangle would correspond to what parts of other triangles. So what I'm going to do is I am going to label angle P with this blue mark right here, and I'm going to label angle R with this purple mark. Now, like we talked about in the last video, all three triangles in this picture are going to have a right angle. We can see it there, we can see it there, and let me go ahead and draw that other right angle right here. And then they're going to have this blue angle in it and this purple angle. So we can see in the big triangle PQR, we see all those angles, the right angle, the blue angle, and the purple angle. In triangle PQS, I see the blue angle and the right angle here, which would mean that this angle right here is the purple one. So let me go ahead and add that mark there. In triangle QSR, I see the right angle and the purple one, which means that this one right here would be the blue angle. And again, the idea there is that when triangles are similar, all of their angles will be congruent. Their corresponding angles will all be congruent. So all three triangles in this picture are similar, so they should all have the same three angles in them. All right, now we can use those angle markings to set up some proportions of corresponding sides. If you remember, a proportion is where we take a fraction and say it equals another fraction. When we set up these proportions, these fractions are really ratios of corresponding sides. So I'm going to look at maybe the big triangle, triangle PQR, and then this smaller triangle QSR, and I'm going to set up two ratios of corresponding sides and use that proportion to find the length of QS. So for instance, if I look at QS, it is across from the purple angle. So I'm going to put QS at the top of this triangle, this ratio, and then on the bottom of that ratio, I'm going to put the side of the big triangle that's across from the purple angle, right? Because QS was across from the purple angle in this triangle. What's across from the purple angle in this bigger triangle? And it would be 20. So the QS is going to get paired with the 20 because those two sides correspond to each other. They're both opposite the same angle. Then I need to set up another ratio, hopefully where maybe I'm not going to introduce a new unknown, right? If I have another unknown, then I'm not going to have something I can solve. I want to set up this ratio so that maybe there's numbers in both these places, or at the very least, if there is an unknown, it's the same one that I have here, which is QS. So let's look at the top number that we're going to use. Again, that is from this smaller triangle. The only other side of that smaller triangle, I guess I know two other sides of that smaller triangle. I know the hypotenuse, and I know this side, which is across from the blue angle. But which one do I want to use? If I were to put the hypotenuse up here, the 15, then the bottom number here would have to be the hypotenuse on the big triangle, and I don't know that length, right? I don't know how long PR is. So I don't want to go 15 over PR because then I'd have another unknown. So instead of using the hypotenuse, I'm going to use this side, which is the side across from the blue angle that's 9 units long. I'll put that right there. And then the bottom number in this ratio is going to be the side that's across from the blue angle in triangle PQR, which I can see if I go across from that, I'm going to have 15. So I'll have 15 down there. And so what I now have is a proportion with only one unknown value. And so I can solve this by cross multiplying. I'm going to take the QS times 15 and say it equals 20 times 9. I just cross multiplied these two and then these two. So let's simplify 20 times 9 and make it 180. So now QS times 15 equals 180. I'm going to divide both of these sides by 15. So QS equals 180 divided by 15, and that's going to give me 12. So I now know that QS has a length of 12. QS equals 12. The second part of this problem asks me to find PS. So what I'm going to do is I'm going to use the same idea that I used here, where I'm going to try and set up a proportion, but now I want PS to be the unknown. So I'm going to kind of set up the framework for this proportion. Fraction equals fraction. I'm going to put PS in this top location, and then I need, for the bottom location, I need to match where PS is. So PS is across from the purple angle. So I need to either look at this triangle, the smallest one in the picture, or the biggest one in the picture, and use the side that's across from the purple angle, because that's where PS is. So let's come over here to this triangle, and let's use 12, right? That's across from the purple angle in the smallest triangle. So I'll put PS over 12. Then I need to set up another ratio using this pattern of like what I call the medium triangle, triangle PQS, over the small triangle, triangle QSR. So the only other side of the medium triangle that I know, well, I guess I know two other sides. I could either use the 20 or the 12. Let's go ahead and use the 20, which is the hypotenuse of that medium triangle. So I'm going to put that in the upper location of this other ratio. Again, when I make up my ratios, I need to use the same pattern in terms of which triangle is on top and which triangle is on the bottom. So that's why the 20 went on top here, because PS was coming from the same triangle that I'm using the 20 from. Now the bottom is going to be the hypotenuse of the triangle where I got this 12 from. And if you remember, that was from triangle QRS. So what's the hypotenuse of that one? It's 15. So that 15 will go on the bottom. And now if I cross multiply this, I would have PS times 15 equals 12 times 20. And so now if I simplify, I'll have PS times 15 equals 240. And then I'm going to divide both of these sides by 15. And then PS will equal 240 divided by 15. Grab my calculator real quick. It tells me it's going to be 16. So PS has a value of 16. Now here's our second example. It again looks very similar. The picture starts with us with a right triangle where we've drawn the altitude from the right angle across to the hypotenuse, creating our three different triangles now. I'm going to label these angles again. I got the blue angle, I got the purple angle. This would mean there's a blue angle there and a purple angle here, and of course there's a right angle right there. So now all three of my triangles use the right angle, the blue angle, and the purple angle. And now we have to find CD. Okay, now this is different because in this picture I only really know two values. So if I want to find CD, let's look at some possible ratios, some possible proportions that I could set up with CD. So let me grab my black pen and set up the framework, and you'll notice here what I've done is I've drawn three ratios that are all equal. So first I'm going to compare maybe these two triangles, and I'm going to set up some ratios between these two triangles, all three ratios of corresponding sides. So I'm going to I'll put the smaller triangle on the top for all three ratios, and I'll put this medium triangle on the bottom for all three ratios. So let's jump in and do that. So on the small triangle, let's start with the hypotenuse. That would be segment BC. I don't know it, so I'm just going to put BC. Then I have the side across from the purple angle, which is CD. I don't know that, so I'm just going to put CD. Then I have the side across from the blue angle, which is 3.6. So I went hypotenuse across from the purple angle, across from the blue angle. Now I'm going to do that same pattern for the medium triangle here. So hypotenuse of the medium triangle is AC. Across from the purple angle of the medium triangle is 6.4. And then across from the blue angle in the medium triangle is segment CD, which I don't know the length of. So now if I investigate these three proportions, is there a way that I can pick two of them out and only have one unknown value between those two ratios? So for instance, if I looked at just these two ratios, that wouldn't work because I'd actually have three unknown values if I was just isolating kind of these two ratios. And if I tried to solve that proportion with these two ratios, I wouldn't be able to do it. There'd be too many unknowns. Same way if I did the first and the last one, right? Then I'd have BC, AC, and CD that I don't know. But you'll notice that if I use these two ratios here, there's two places that are blank that don't have numbers, but it's the same unknown in both places. So what I can do is I'm going to just kind of temporarily ignore this ratio, and I'm just going to solve this proportion right here by cross multiplying. Now that's going to take CD and multiply it times CD, and then it's going to take 6.4 and multiply it times 3.6. So CD times CD is going to be CD quantity squared, or CD squared. And 6.4 times 3.6 is going to give me 23.04. Now what I want to do is I want to do the square root of each side. I'm going to do the square root of CD squared and the square root of 23.04. That's going to give me just CD, and then the square root of 23.04 is going to give me 4.8. So now you can see I know the length of CD is 4.8. In this final example, we have another similar picture with the altitude from a right triangle being drawn from the right angle across to the hypotenuse, creating our three similar triangles. Let's go ahead and label our angles. Blue angle there, purple angle there. Oops, I forgot to change to purple. Let me undo that real quick. Purple angle there. That means blue angle will be here and purple angle will be there. Let's put our values. AD is 64 and CD is 48. And so now what we want to do is, again, we're trying to find BD right here. But let's look at these two triangles and let's set up our ratios. Let's put the smaller triangles side lengths on the top and the bigger triangles side lengths on the bottom. So first I'm going to take the hypotenuses of each. Hypotenuse of small triangle is BC. Hypotenuse of medium triangle is AC. Now we'll go across from the purple angle. Across from the purple angle in the small triangle is 48, and across from the purple angle in the medium triangle is 64. And then we'll go across from the blue angle. Small triangle first, BD, medium triangle, 48. And so now you can see these are the three ratios that I have for these two triangles and their corresponding sides. I'm trying to find BD. I want to pick out two of these ratios and pick out two that will leave me with just one unknown value between the two ratios. So you can see here, this first ratio has two things that I don't know. So anytime I'm going to use this ratio in a proportion, I'd be in the situation that I don't want to be in because I'd have two unknowns. But you'll notice here, if I pick out these two, right, if I use these two ratios, my only unknown is BD, which is what I'm trying to find. So let's go ahead and do that. Let's do 48 times 48 equals 64 times BD. Simplify 48 squared, or 48 times 48, and we get 2,304. So that equals 64 times BD. Now I'm going to divide both sides by 64. 2304 divided by 64 is going to give me 36 for the length of BD. And there I have my answer. BD is 36 units long.